The problem statement that we chose to tackle as a group was the driverless car. Human error is a huge problem in accidents involving motor vehicles. According to NHTSA's survey, human error is the critical reason for 93% of all vehicle crashes. The solution is the driverless car because computers can't drink, can't text, and can't get distracted by things that make us human. The most basic concept in the driverless car is controlling the car's velocity. The control system responsible for making the car driverless must account for the force from the engine, the drag and the friction, the car's mass, the disturbance forces, and the position of the car. This is the basic diagram for the driverless car, which in turn turns into this, which is the impedance network, which we can get the transfer function, which is x c of s over f engine of s equals 1 over bs plus ms squared. However, we need the velocity, not the position, but that's a derivative, so in turn we can get vc of s over f engine of s, which equals 1 over b plus ms, which is our transfer function related to velocity. And when you plug in our values, which m equals 1800 and b equals 200, we get vc of s over f eng s equals 1 over 200 plus 1800s. And from there, we also know that our F engine equals 2,000 newtons, which gives us our step response diagram.
So now that we have our initial plant design, the next step is to kind of do some analysis on where our plant is before we apply the controller. So the transfer function of our plant g of s is 1 over ms plus b, and we can see that we have this pole of ms plus b. This pole is going to stay on this left-hand side of the complex plane and remain stable as long as b is a positive value. And in terms of the physical realities of our system, we can reasonably say that the damping value is always going to be positive, so we can say that this system in this configuration is stable. This is also represented by this root locus plot, which is done with, as before, a mass of 1,800 kilograms and a damping value of 200 newton seconds per meter. Now, with this initial plant, some of the metrics that we're seeing, we have a rise time of 19.8 seconds, a percent overshoot of 0%, and 0 steady state error. Now, the typical disturbance that we're going to face in the US, the typical maximum road grade is 6%, which translates to about 3.43 degrees. So we can see here that when we're going up a road, our car moving this direction, if it's sloped, we're going to have a disturbance force opposing the direction of our movement. And if we're going down a hill with the car moving this way, we're going to have a disturbance force in the direction of our movement. Now, assuming that we're going to encounter roads with negligible concavity, that is, negligible rate of change of the slope of the road, we can model this disturbance as a reference input with value mg sine theta, which for these values would be plus or minus 1,056.5 newtons. So as long as we are assuming that we encounter roads that have negligible concavity and can be modeled as a constant slope, then this is going to be the maximum disturbance we'll face in either direction.
The next step in our design process is actually the designing of the controller. As you can see here, this is our block diagram for our system. We have the transfer function, the controller, we have our feedback loop, our input and output, and then we also have the disturbance in there. The next on the list was the design criterion, or the metrics. We chose a rise time of about 7 to 10 seconds, and the reason we chose this was basically from a personal experience. My car does 0 to 60 in about 5.4 seconds, and that's if I'm flooring it. So we decided that 7 to 10 seconds is a comfortable 0 to 60 time, and especially because it's especially comfortable if you're not the one driving the car. The next criterion was the percent overshoot, which we wanted to be less than 5%. The reason that we wanted a less than 5% overshoot was because If you have an overshoot of 5% going 60 miles per hour, that's 63 miles per hour. And we figured that 3 miles per hour over the speed limit is, you're most likely not going to get a ticket. The final design criterion was we wanted a steady state error of 0. And the reason that we wanted this was because you don't want your system to hit its desired output, then fluctuate at different speeds. In order to meet these design criterion, we had to choose a controller. The reason that we didn't go with a PD controller or proportional derivative controller is because these controllers are typically used to dampen oscillatory systems, and we did not expect an oscillatory output for our system. So this is why we chose proportional integral controller. The proportional integral controller allows us to attain 0 steady state error while also meeting our other design criteria. The way that the proportional integral controller attains 0 steady state error is by adding an integrator to our system. This is seen with the low frequency gain evaluated at 0. The low frequency gain is evaluated at 0, so you get this integrator here. If you plug in 0 for S, this right here is going to go trend to infinity. Then, once we plug the low frequency gain into the steady state error function, 1 over 1 plus infinity is going to go to 0. After we chose to go with a PI controller, we moved over to the CISO tool in MATLAB. Here we were able to emulate a controller by adding an integrator here and a 0 here. Next, moving over to the step response graph, we added metrics including the rise time, which is shown with this line here, and the percent overshoot with this line here. After we added those metrics, we manipulated the 0 here and the gain of the controller in order to meet these metrics while also allowing for a little bit of wiggle room for the disturbance that we would model later. From here, we got to this controller equation where our KP is 321.894 and our KI is 53.649.
So for our verification and iteration phase, we're going to take a look at some of the responses that we got from our controller. So this is a CISO tool modeled step response with 0 disturbance, and this is a Simulink modeled response with maximum disturbance in the uphill configuration. Both of these are set with a target velocity of 30 meters per second, which translates to roughly 70 miles per hour. So if we look at some of the metrics that we got from these 3 different configurations, 0 disturbance, maximum uphill disturbance, and maximum downhill disturbance, we can start with our 0 disturbance case, which we talked about earlier. We have our rise time at 8.61 seconds, percent overshoot of 3.53%, and 0 steady state error. And of course, that 0 steady state error is going to remain consistent throughout all of our configurations due to our integrator. However, we're going to get some changes when we move to the uphill configuration. Our rise time, because we have this force opposing the direction of our velocity, is going to increase to 9.67 seconds. However, our percent overshoot, because we have that opposing force, is going to decrease to 2.44 seconds. If we switch over to the downhill configuration, where we have the force in the direction of where our car is trying to travel, we're going to get a rise time that drops down to 7.63 seconds, but a percent overshoot that slightly exceeds the bounds of our specifications at 5.03%. Now, for the purposes of this controller, we're going to say that this 0.03% exceeding of our specification is acceptable, and that's because in order for us to be able to handle the maximum configuration in both uphill and downhill, we're going to have to account for the variance in downhill. The overshoot is going to get really large, and in uphill, the rise time is going to get very large. If we were to alter the controller, we would start increasing this 9.67 second rise time. So instead of moving the error in handling both configurations over to this uphill rise time, we're going to accept a 0.03% exceeding of our overshoot.
The final portion of the project was to analyze the robustness of our system. As you can see here with the Bode plots from our input to our output, the gain margin is infinite because the phase plot never touches negative 180. To calculate the phase margin, we went to 0 degrees, 0 decibels, and then came down. And in the CISO tool, we found that the actual phase margin was 91.3 degrees at a frequency of 5.72 radians per second. Then we calculated the time delay that the system could handle, and after rearranging and solving, we got that the time delay is 0.279 seconds. Finally, we plugged that into Simulink with this time delay operator, and in here we plugged in 0.25 seconds to see how our system would react. And as you can see in this graph, our system did not go out of control. We did have a slight rise in our percent overshoot as well as our rise time, but overall our system is still stable.